we go for fourth phase of the compiler is the intermediate code generation. Intermediate code generation is the fourth phase of the compiler. After the syntax and semantic analysis, some compilers may produce or generate an explicit intermediate code generation for the given source program. Okay, that means for a given source program, after the syntax and semantic analysis, some compilers may produce an explicit intermediate representation of the given source program. The intermediate code representation of the source program has two important properties. First one is it is very easy to understand. Second one is easy to translate into target program. Okay, we can easily translate the intermediate representation of the source program into target program. The intermediate representation of the source program is very easy to understand. Next one is the intermediate code representation can be represented in so many forms. So one of the most important form is tree address code. What is tree address code? Tree address code is a sequence of instructions. Each and every instruction can have at most 3 operands. At most 3 operands is nothing but it may contain 1 operand, it may contain 2 operands, it may contain 3 operands. Okay, each and every instruction may contain at most 3 operands. Suppose we can take a given statement, position is equal to initial plus rate into 60. How we are converting this given statement into tree address code? So here tree address code means each and every instruction or statement contains at most 3 operands. Okay. So for example, this is the statement. So this statement can be converted into tree address code. So first one is temp1 is equal to int to real of 60. Okay. So in this one, highest priority given to into operator. So for that one, first we are converting the integer 60 into real by using int to real operator. So that is temp1 is equal to int to real of 60. Okay. Second one is after converting this integer 60 into real, it can be multiplied with the identifier rate. Identifier rate can be treated as ID3. ID3 into whatever the result we are getting, that is temp1. So ID3 into temp1, that can be assigned to temp2. So now we are getting this result. First, temp1 is equal to int to real of 60. That is the first statement. Second statement is whatever the result we are getting, that result is multiplied with identifier ID3. Whatever the result we are getting, that result can be assigned to temp2. Okay. Next, whatever the result we are getting after this temp2, that can be added to the identifier ID2. So this is this result is ID2 temp2. Temp2 can be added with ID2. Here ID2 is nothing but initial. Okay, this result can be assigned to the variable temp3. Okay, now whatever the result we are getting, this is the total result is temp3. Temp3 can be assigned to the position. Here position is nothing but ID1. So here temp3 can be assigned to the ID1. So each and every instruction can have at most 3 operands. So here 2 operands are there, here 3 operands are there, here 3 operands are there, here 2 operands are there. Okay. So these instructions fix the order in which operations are to be done. Here we have to fix the order in which operation are to be done. Next one is fifth phase of the compiler is code optimization. Here mission independent code optimization. Here we have to use mission independent code optimization. Here mission independent code optimization attempts to improve the intermediate code representation to get the better target code. Okay, we can get the better target code by improving the intermediate representation of the source program. That can be done by mission independent code optimization. In some compilers, the code optimization followed by intermediate representation to get the better target code. Next, the above optimized code. Next, the above intermediate code representation. Next, the above intermediate code representation can be optimized in these two statements. In the intermediate code representation, the first instruction is temp1 is equal to int2 real of 60. Second instruction is temp2 is equal to id3 into temp1. Okay, here the conversion of integer 60 into int2 real, that is 60.0, can be done all at once at compile time, so that instruction can be eliminated. Okay, next one is final result temp3 can be assigned to identifier id1. So this instruction is also eliminated. So whatever the result we are getting, that result can be directly assigned to id1. Okay, the above intermediate code representation can be optimized into these two instructions. So first one is temp1 is equal to id3 into 60. Okay, so in the intermediate code representation, the first instruction temp1 is equal to int2 real of 60, that can be eliminated. Next one is, so temp1 is equal to id3 into 60. Okay, this is the second instruction in the intermediate code representation. By eliminating the first instruction, this is the second one. Temp1 is equal to id3 into 60. Now whatever the result we are getting, that is temp1. Temp1 means id3 into 60. This means is id3 into 60. Whatever the result we are getting, that result is temp1. This temp1 can be added to the identifier id2. Whatever the result we are getting, that result can be assigned to id1. Okay, so I will show temp1 is equal to int2 real of 60. Temp2 is equal to id3 into temp1. id3 into temp1. Next, temp3 is equal to id2 plus temp2. Next one, id1 is equal to temp3. So this is the intermediate code representation. So this statement can be eliminated because at the compile time all the instructions at once that are converted into real, so that this instruction can be eliminated. Next, this is direct instruction. So now temp1 is already, this instruction is already eliminated, so it can be written as temp1. Temp1 is equal to id3 into temp1. Temp1 result is directly 60.0. So therefore this instruction can be written as temp1 is equal to id3 into 60.0. Next one, this is temp1. Now we can take temp2. Temp2 is equal to id2 plus here whatever the result we are getting, that is temp1. So that can be directly assigned, and this instruction is also eliminated because whatever the result we are getting at instruction 1, that can be directly assigned to id1. So these 4 instructions are intermediate code representation. This intermediate code representation can be optimized into these 2 instructions by eliminating this one and by eliminating this one. Only 2 instructions are optimized code instructions for the given statement. Position is equal to initial plus rate into 60. Okay. Next, go for last phase, that is the 6th phase of the compiler, that is code generation. Code generation is the final phase of the compiler. In the code generation phase, so whatever the intermediate code representation of the instructions that are converted into some optimized form. Okay, so whatever the result we are getting at the 5th phase of the compiler, so that is the input for the code generation phase. So here the code generation phase converts the given intermediate optimized code into the target code or mission instructions or assembly code instructions. Okay, the code generation phase converts the intermediate code instructions or optimized code instructions, each instruction translated into a sequence of mission instructions or assembly code instructions. Okay, whatever the optimized code we are getting through code optimization, that can be converted into a sequence of mission code instructions or assembly code instructions. Okay, the memory required for each of the variables that can be assigned by the program. So the program can assign the memory for each and every variables that are used in the instruction. Okay, next, here for the given optimized code, so what is the code generation phase? Code generation phase generates. The code generation phase generates the target code for the given optimized code by using 2 registers, that is R1 and R2 registers. Okay, so in this one, the source operand, that is the source operand is this one. The source the first register, the first operand specifies the source. The second operand represents the destination. Okay, this is the source and this is the destination. This is the source, this is the destination. Okay, so in this one, F denotes the each and every instruction deals with floating point representation. Okay, first one is move F id3 R2. Okay, whatever the ID3, the content of ID3 can be moved to R2. So now R2 contains, that is ID3. ID3 is rate, identifier rate. Next, multiply has 60.0 with R2. Okay, so now R2 contains, so rate is multiplied with 60.0. So now initially the register R2 contains only identifier ID3. Okay, now after the second instruction is completed, so hash 60.0, that is the converted real number 60.0 is multiplied with the identifier ID3, that is rate. Now the result is, so rate into 60. Okay. Next one, move F ID2 comma R1. So now R1 contains ID2. ID2 is initial. ID2 is initial. Next one, add F R2 comma R1. So now R1 contains initial plus R2. Okay, initial plus R2. Initial is identifier ID2 plus R2 means rate into 60. So now move F R1 to ID1. So now ID1 is equal to, so initial plus R2. So that means initial plus ID3, that is the rate into 60.0. So the final result is there at ID1. So this is the ID1 is equal to ID2 plus temp1. So ID2 is initial, temp1 is nothing but rate into 60. Here the first one deals with the source operand, the second one deals with the destination operand. Here F means each and every instruction F contains that deals with the floating point instructions. In the above optimized, in the above target code, each and every instruction contains F. F deals with instructions or deals with floating point numbers. Next, hash 60.0 represents the constant. If the symbol hash before 60.0, then it can be treated as constant. Okay. So next one is symbol table management. So symbol table is a data structure that is used for storing the identifiers as a record. So here each and every record can be allocated for identifiers. Okay. Next one is, so each and every identifier has some fields. In that fields we have to store the attributes of the identifier. Okay. So a symbol table is a data structure. In that data structure, a record is there for each and every identifier, and also some fields for storing the attributes of the identifier. Okay. This data structure allows to store the identifiers and to find any identifier so quickly. So that means to access the identifier as early as possible. For that purpose, we have to use this data structure. Okay. And also we have to store the identifiers and its attributes in that record. For that purpose also we have to use this data data structure. So that means the data structure allows to find or to identify any identifier and to store or retrieve the attributes of each and every identifier. Okay. So next one is, what are the various attributes of identifier? So it's a type. What is the type of that identifier? It's a scope. What is the scope of that identifier? Storage allocated for the identifier. So on which place the storage is allocated for that identifier? So type, scope, storage allocated for the identifier. So these are the attributes of each and every identifier. So now we have to store in records the identifier and its attributes that have to be stored as a record in a symbol table. For example, we can take this statement, position is equal to initial plus rate into 16. So this is the symbol table. In this symbol table, we have to store the identifiers. The first identifier is position. The second identifier is initial. The third identifier is rate. Okay. So it has, each and every identifier has some fields. In that fields, we have to store the attributes of the identifier, type, scope, storage allocated for the identifier. Okay. Okay. Next, an essential function of the symbol table management is to store the identifiers as a records and also the attributes of each and every identifier also be stored in the symbol table. Next one is the error handler. So the main function of the error handler is to detect an error in each and every phase. After detecting an error, so that phase must deal with that error, then the compiler proceeds its compilation. Okay. After that, if any error is detected, then it can easily deals with that error. Symbol table, both symbol table management and error handler interact with all the phases of the compiler. Next one, mainly a large number of errors that are detected or that will occur in syntax and semantic analysis phase. Okay, these two phases can handle more number of errors that are occurred in these phases. So now the 6 phases are completed. Next, symbol table management and error handler are also discussed in this video. Now, these 6 phases, how the given statement is translated. Suppose we are taking this statement, how this statement is translated in the above 6 phases. Position is equal to initial plus rate into 60. So this statement can be given to the lexical analyzer. The lexical analyzer can divide the given statement into some tokens. So that is, position can be taken as token ID1, initial can be changed as token ID2, rate can be changed as token ID3. So now this is the output of the lexical analyzer. ID1 is equal to ID2 plus ID3 into 60. So this can be given as input for the syntax analyzer. The syntax analyzer can represent the above tokens in parse tree. So this is the given parse tree. The output of the syntax analyzer is parse tree. So this parse tree can be given as input to the semantic analyzer. In the semantic analyzer, this can be converted into real. So here by using the operator int to real. So that is 16. So this tree is the output of the semantic analyzer. So this can be given to the input for intermediate code generator. This intermediate code generator can convert it into these statements. Okay. So these statements are given to the code optimizer phase. So this phase can optimize the above intermediate code into these two statements. Okay. These two statements can be given as input for the code generator. This code generator can convert these two statements into this one. Okay, here f in each and every instruction deals with floating point numbers. Hash 60.0 can be treated as constant. Finally, this is the output for the given statement. Now, whatever the identifiers are there, these identifiers are stored in the symbol table as a record. Okay, so each and every identifier has some number of attributes. So these attributes information is also stored in the fields for each and every identifier. What are the attributes for each and every identifier? It's a type, it's a scope, and storage allocated for an identifier. So if any error is occurred in the given phase, so that phase deals with that error and correct that error. Okay, for that purpose we have to use error handler in each and every phase. Okay, so whatever the identifiers are there, that identifiers are stored in the symbol table. Okay, both symbol table management and error handler interact with all the phases of the compiler. So this is the description about the phases of the compiler and its example. If you like this video, please subscribe my channel name. So DIVVELA Srinivasa Rao. DIVVELA Srinivasa Rao.